Hi guys. So in the last video what we looked at was loans and mortgages, and in this one we're going to look at investments, annuities and bonds. So I just want to go back to what we did in the previous video and just look at the idea of the loan and the mortgage on a timeline. So what we had was this, and what we were doing is we were borrowing a lump sum of money here right at the beginning, and then we were paying it back the same amount for so many months or so many years into the future. And what was happening there was everything then was coming back. So this we were bringing back. So suppose we had borrowed 200,000 in a mortgage, and we were given 200,000 up front. So at this time here we're given 200,000, and then we're paying back that 200,000 in a whole load of payments plus the interest here. So this is coming back. And remember, if it's coming back, i.e. this is coming this way, this is coming back, and so on and so forth, everything's coming back, that last one's come back all this way, that we were discounting them by how many time periods they were coming back. What I mean by discounting was, what we were saying was that this was a over 1 plus I, this was a over 1 plus I squared, etc. And this was a over 1 plus I to the power of n, or t. And that there was a loan or a mortgage. What an investment is it works the other way around. So what's happening here is, if I just draw the timeline for you again, just a bit back in black. What we want is we want to have a lump of money at the end there. So if you think about it, when I'm saving for my pension, what I'm doing is I'm putting in a whole load of payments or savings. So for example, I'm putting a saving in today of some amount, saving in next month or next year, and so on and so forth. And so on and so forth. And what's happening is, instead of going to the left like we're doing up here, so here what we're doing is we're bringing every payment to the left, which means that we're discounting it. For this one, what we're doing is we're taking every payment to the right, which means it's going to increase, because what we're doing is, we say we're trying to get 200,000 here. What we're doing is we're investing money as we go along. So you can see here what we're doing is we're investing this amount of money, so it's going to increase, which what's going to happen here is we're going to get 1 plus I to the power of something. And again, this is going to be 1 plus I to the power of something. So say that it was 20 years, this is going to be 1 plus I to the power of 20, 1 plus I to 19. And this last one, and this is important, this last one gets 1 plus I to the power of 1. It gets one sort of time period where it's allowed to make some money. So hopefully this will give you an indication on the sort of differences between how we set up a mortgage or loan and an investment sort of scenario. Okay, so let's have a look at this example. There's a lot going on here, so let's just quickly read through it. It says Eric starts a savings policy. He starts by saving 100 now. Each year the value of the saving he makes grows by 4% to take account of inflation. He makes 20 annual savings, and his policy matures at the end of the 20th year. Throughout this period, his fund is guaranteed to gain interest, an annual effective rate of 3%. And there's a few things that we're going to be doing here. First thing I'm going to do is just draw a number line just to show what's going on here. So what we have is, there's my number line, and he wants to know what his end rate is going to be here. Okay, and he's going to be saving money every year for 20 years. So look, you can see there's the first year. Leave a nice big gap, guys. There's the second year, and then that's going to keep going. Be happy with that. And then the last year before, and I'm just going to leave it like that so you can see what's going on. Now this is going to be my F1. It says obtain the value expression for F1, the value of his first payment when the policy matures. F1 is here. That's going to be my F2, and we'll just leave it at that for now. And what we've got to try and do is going to try and work out what this is going to be worth. So what this here is going to be worth over here when it comes out. This particular payment. Okay, so we know for F1 what he's doing is he's sticking in €100. Okay, so you can see that this payment here is going to be €100. That's what it says. Now, we know that the interest rate is going to be 3%. So that's going to increase by 3% every year. So 1.03. So be happy with that. So the 100 that I put in today is going to increase because it's going to the right. It's heading towards this dot here. It's going to increase by 3% every year, and it's going to be for 20 years. Okay, so it's got 20 years of growth coming into it. So that's 20. So that's my F1, boys. So that there is now done. Okay, now you can stick that into your calculator if you want, and you get an answer. F2 now, the value of the second payment. Well, let's just read what it says here. It says he starts by saving 100 now. Okay, so there's the 100. Each year, the value of saving he makes grows by 4%. So he's going to up his payment from 100. He's going to add 4% to that. But he's going to keep doing it every year. Okay, so how do we add 4% to the 100? That's easy. So we've got 100. If we multiply that by 1.04, that's adding 4% to that. But then what you've got to remember now is that this now is going to move to here. And instead of moving 20 times at 3%, it's going to move 19 times because it's one less than this payment here. So this now is going to be multiplied by 1.03 to the power of 19. So everybody happy with that? So just explain that again. So what we have is 100. She's putting in 4% extra to account for inflation. So there was no inflation from this one. For this one, there's a year of inflation, which is 1.04. And now there's one less compound at 3% because it's taking a year less. It's not taking 20 years to get from here to my dot now. It's taking 19 years because there's only 19 years of growth. So everybody happy with that? Okay, if you have a look at F20. Okay, so this one here, the last one, which is we'll call that F20. Okay, that's way down. So F20, what we have here is that, so I'm going to red again, we've got the initial 100. We've put in 4% each year for inflation. So have a think of how many times we've done that. Well, here there was no inflation. For F2, there was 1 year of inflation. For F3, there'd be 2 years of inflation. So you can see here that the number of years of inflation is essentially n minus 1, yeah? So F1, no inflation. F2, what we have is we have 1 year of inflation. F3, we'd have 2 years of inflation, so on and so forth. So this is going to be multiplied, to the power of 19, because we've got 19 years of inflation. And then we have 1.03, because we're going to be able to invest that at 3% per annum. But notice here, guys, look, it's only getting 1 year. Okay, so it's only getting 1 year from here to here. So that's 1.03 to the power of 1. Now the last thing it says is determine the value of Eric's savings policy when it matures, i.e. what's the value of this? So what is the value of the dot here? So when we add up all of these, so essentially what we are doing is we're adding up for IV, okay, we're adding up F1 plus F2 plus F3 plus all the way to F20. So hopefully you can see there that what we have is we have a geometric sequence. And if I put in the numbers here, you can see my F1 is, in blue, 100 by 1.03 to the power of 20 plus F2, which is 100, 1.04, 1.03 to the power of 19, plus if I did F3, it would be 100, and it'd be 1.04 to the square, and it'd be 1.03 to the power of 18, and the last one is 100, you can see there 1.04 to the 19 multiplied by 1.03. So that there, guys, is our geometric progression. Now, you've got to remember that S of n is equal to A1 minus R to the n over 1 minus R. So we now need to calculate our A and our R. Well, our A should be straightforward. This here is going to be my A. So A is equal to, and we've got 100, 1.03 to the 20. So that's easy. Now our R, how are we getting from this one to this one? And if you remember when we back ages ago when we looked at sequence and sequences, what we would notice that R is equal to term n plus 1 over term n. So we can say that our R in this case is equal to term 2 over term 1. That's what should happen. Okay, so if we do that, we get In this particular case, we've got 100, 1.04, and 1.03, power of 19, all over 100, 1.03 to the 20. Now guys, hopefully you can see this is 100 is going to cancel, and you can see here on the top we have 90, so you get to the power of 19 to the power of 20, which means that all of these are going to cancel. I'm going to be left with 1.03 on the bottom, which now means that what we're going to end up with is 1.04 on the top divided by 1.03 on the bottom, and that there is my R. You can put that into your calculator and put it into one of your memory function buttons, and if you do that you should get 1.0097087, I believe. Okay, so now that we have that, we have our A, we have our R, we just need to stick it into the formula. So S of n is equal to our A, which is 100 by 1.03 to the power of 20, multiplied by 1 minus r to the n, so 1 minus r, which was 1.0097087. The power of n, well, it's 20, because it's 20 years for this. Okay, so that's what we're doing. All over. And it's going to be 1 minus r, so 1 minus 1.0097087. You stick it in your calculator, guys, and if you do that, you'll get S of, well, it's S of 20, not S of n. S of 20 is equal to 3965.6221. Oh, sorry, 2 decimal places. So when this policy matures at the end of 20 years, Eric will have €3,965.62 in the bank. So hopefully that made some sense. This is your bog standard sort of leaving cert question. What they get you to do is they tell you that somebody's going to retire in so many years' time, that they need to save a fund of so much, equal annual savings. They normally do it monthly, guys, making it a bit more difficult. And then once they've saved the 600,000 in this case, what they then do is you have what's called an annuity. So you cash that in, and then you get a load of savings in order to live the rest of your life in retirement. So let's have a look at this example too. So it says Larry's going to retire in 24 years, wants a fund of 600,000, equal annual savings. It's going to make this a bit easier, starting now. So that's important to starting now. It's always starting now, guys. I'm finishing 1 year before he retires. It always finishes 1 year before the retirement as well. AER is 4% and 600,000 is what we've got. So again, first thing we do is we draw a timeline. And what we want at the end of this, we want to take out 600,000. Okay, and we're going to be making equal annual payments, or equal annual savings, I should say, of A, etc. And we're going to have 1 just before the end, so we're just going to put dots there to show there's a whole load of payments before then. And we are heading to the right. So everything is coming from left to right, which means that it's increasing in value. So we're told that T is equal to 24. So that first payment is going to be whatever the interest rate is. And in this case, it's 4%. So this is going to be 1.04 to the power of 24. Because it's going to get 24 years of growth. This one here is going to be 1.04 to the power of 23, because it's going to get 23 years of growth. And that last one is going to be 1.04 to the power of 1, because it's going to get that final year of growth. And all of these payments must add up to 600,000, because that's what I want to have in my retirement fund at the end of 24 years. So let's write this now as a geometric sequence. So hopefully you can see that what I have here is A 1.04 to the power of 24 plus the amount by 1.04 to the 23 plus, I'm just going to keep going to get to that final savings amount there, 1.04, which is being saved for 1 year, and that's got to equal 600,000 euros. Now what I'm going to do is I'm going to swap them around. So all I'm going to do is I'm going to put A to the 1.04 at the front plus A to the 1.04 squared plus A to the 1.04 to the power of 24, and that's equal to 600,000. So what I've done here is I've just moved this to here, the square to here, and I've just rewritten that top line there, so it's easier to work with when we come to look at working out the geometric progression in a second. So we know that, or we should know, that S of n is equal to a1 minus r to the n all over 1 minus r. So let's put the numbers in for that. We need to find out our a. Well, our a is the first term, so that's our a, that's easy enough. And guys, hopefully you can see that to get from a multiplied by 1.4 to a multiplied by 1.04 squared, and all we are doing is we are multiplying by 1.04. So our r, our common ratio for this particular one, is equal to 1.04. Okay, let's whack that into the formula. So what we now have is that S24 is equal to, and just put the numbers in. So my a is a by 1.04, and we have 1 minus r, which is 1.04 to the power of n, and my n here, guys, is 24. Okay, all over 1 minus 1.04, and we know that that should be equal to 600,000 euros. What we're going to do now is you're going to stick this in your calculator, so 1.04 multiplied by this, divided by this, and you're going to get a value which you're going to stick in front of the a. So if you do that, the answer you are going to get is 40.64590829 by a is equal to 600,000. Divide both sides by 40.6459, etc., and you get a is equal to 14761.63 to 2 decimal places, and of course we always use 2 decimal places because it's money. Now that means that in order to have a fund at the end of 24 years of 600,000, given the fact that we can invest money at 4%, this person Larry has to make equal contributions of 14,761.63 per year. So every single year, that's what he pays in, and at the end of it, he'll have a fund, a pension fund of 600,000. Okay, part 2. If he waits 4 years, well, this is pretty much the same problem as what we just had. Instead of working at S of 24, we're going to work out S of 20. All of this is exactly the same. So we're going to end up with S of 20 here is equal to A by 1.04 by 1 minus 1.04. But this time it's going to be to the power of 20 all over 1 minus 1.04. And again, that's going to equal 600,000, guys. So all we're saying is it's the same payments. It's just they're only making 20 years of payments rather than the 24. So that's why this n now has changed to 20 instead of 24. And you solve it, guys. I'm not going to go through the mechanics of the maths, but if you do solve that, what you'll find is that the payment is going to be equal to, in this particular one, 19374.09. So I'll leave that as an exercise for you, just to make sure that you get this answer solving this particular equation. Okay, an annuity. So an annuity is a term which refers to a regular series of payments made from a fund. Guys, essentially what an annuity is, it's all this rubbish you can read, but essentially what it is when you get to the stage where you have a retirement pot, just like we had in the previous slide, so you get 600,000, what you do is you go around to the banks or a financial institution and you say to the bank, I have 600,000, I want to have a number of regular payments, what would you give me? So what you do is you essentially give the bank the 600,000 and they change it for a monthly or yearly, depending on where you go, monthly or yearly amount. So your 600,000 might be worth 14,000 a year for the next 20 years or whatever. Okay, so that's essentially what you're doing. Now, in your exam, what generally they ask you to do is to work out somebody's retirement fund, which is what we did in the last slide. And then what we have then is, okay, given that they have a retirement of X, work out what they're going to get monthly when they cash in an annuity. Okay, so let's have a look at the next example. So it says, Sheila's accountant Marie has informed her on the day of retirement she'll have a fund of 467,500 to buy a pension annuity. She'd asked Marie to make calculations about different possible annuities. The AER at the time is 4.8, so all the calculations are based on that rate. In answer to Sheila's queries, calculate the following options which can be purchased with her fund. Okay, the value of monthly payments starting on the date of retirement and lasting for 25 years. Okay, so first of all, we're not looking at yearly, we're looking at monthly. So that's the first thing you've got to be aware of. Okay, so 25 years, we're already told that's 300 payments, that tells us our N, and it says starting on the date of her retirement. Now, what you'll find is with an annuity, it will always start on the date of retirement. Okay, so if you think about it, just to go back to our previous slide, what's happening here is when we were doing a quick timeline here, this is from the previous slide, suppose when we had the 467,500 and our last savings was here, wasn't it? Yeah, so this was our final savings, which then got 1 year of interest. So when she gets to this particular point in time, when she retires, so there she is with her 46750. Okay, what she does is she gives that to the bank. So the bank takes the 467,500, but then gives her a payment on that day. So that there is the amount she gets paid, and then that keeps going, and going, and going, and going. Okay, and that'll go on for however many years, or it could go on until she dies. Depends on what she's agreed with the bank. Now she's agreed with here. This is going to be 300 payments, or lasting for 25 years. But notice, and this is really important, that the first payment is on the day that she takes the annuity. So unlike before, which was a loan, what happened was the first payment for a loan was one time period afterwards, wasn't it? Yeah. For an annuity, it's on the day that you get the annuity. And it's really, really important that you remember that, because otherwise you'll get it wrong. Okay, so let's look at this timeline again. You can see that all my amounts now are to the right. I've given the money here, this 467,500. It's like giving a loan to myself, if that makes sense. So what I'm happening now is that all of these are coming to the left to get to this black thing here, to get to this money. So therefore, they're all being discounted. Okay, and that's important. So what's happening here is all these values are coming to the left. So therefore, when we're looking at an annuity, all of the values are being discounted, apart from this one, because this is just the same worth, because it's not being discounted we're at the present value of that is actually just A. So this one is going to be discounted by 1 plus I, whatever the interest rate is, we'll work out in a second. This one's going to be by 1 plus I to the square, this one 1 plus I to the cube, and so on and so forth. But there's something really, really interesting at the end of this. If I just take this to the end, that this last payment here, this last A here, it's going to be 1 plus I to the power of whatever your N is minus 1. Now there's 300 payments here, because that's what's being told up in the question up there. So this is actually going to be 299. And the reason this is, guys, is if you think about it, what we had before was for the loan, our first repayment started here. So this was discounted once, twice, 3 times, etc. But our first payment is actually on the day, and that's not being discounted at all. Which means that the final payment isn't going to be discounted 300 times because we've already made one payment on a day. It's only going to be discounted 299, i.e. N minus 1. Okay, so a lot of people forget that, and a lot of people go A over 1 per side to the 300. So just make sure that you remember that if we do have a annuity, because this first payment is taken on the day, this first A here, that means that this one is only being compounded 299 times, and therefore it only gets discounted 299 times on the way back. Okay, so that's something that a lot of people forget. So let's have a look at the interest rate that we're going to use for this question. Now we're told the interest rate is 4.8%, but that's the AER, and we're doing this monthly, so we have to change this yearly or annual rate into a monthly rate. Done that in a few of the previous videos, so that shouldn't be too much of a hassle for you. So what we have here is we take the yearly rate, which is 1.048 to the power of a 12th, and we minus 1. And if we do that, we get the answer of 0.048. 0.003914608. So that there is my interest rate for this particular setup. Now, we did a little trick last time where what we said was well, okay, we'll let v equal to something just to make the formation of the geometric progression easier. So we're going to say we'll let v equal 1 over 1 plus I here. And you can whack that into your calculator, guys. You can put that in, and I save that to one of your buttons, you know, the memory buttons. Okay, so if I do that, I'm just going to say that this is going to be a, and we're going to get plus av plus av squared plus av cubed plus, and it's going to go all the way to av to the power of 299. Okay, this just makes life setting up the GP a bit easier. So we can see here that there must be equal to 467,500, and what we're going to be doing is going to be solving for a. Well, we can see here that my a is just a, that's my first term, and my r is equal to v. Okay, so it's just a case now of sticking it into the formula. The formula is S of n is equal to a1 minus r to the n all over 1 minus r. So what we have here is, this is still 300 payments, guys. So again, this is another mistake that people make. It's S300. Okay, it's not S299, it's S300. There are still 300 payments, even though the fact is that this has only been discounted 299 times. So there's another mistake people will do. They'll put, instead of putting S300, they'll put S299 because they're looking at this. There are 300 payments. That there is in the question. So make sure you don't make that mistake. Okay, so then just stick it through. So that's now equal to, and our a is just obviously a. That's what we're trying to find out here. And we've got 1 minus r to the n, so 1 minus v to the power of, I just told you it was 300. Yeah, make sure you get that right. All over 1 minus v. Now you should have your v button, or you should have v saved in your calculator, lads. And then it's just a case of working it out. Now don't forget that's still equal to 467,500. Work that out, you're going to get something in terms of a. Whatever that is, then divide that into 467,500, and you should get that a is equal to 2640.87. So that means that if Sheila has a pot of 467,500 and she takes an annuity at 4.8% per annum, she will receive a monthly payment every month for the next 25 years, starting on that day, of €2,640.87. So let's take a look at part 2. It says the value of monthly payments starting 1 month after, that's important, so 1 month after her retirement and continued indefinitely. Well, that's just a sum to infinity, and the sum to infinity is a over 1 minus r. So let's just, again, once we've been given a bit more information, let's just set up a new timeline. Just going to try and move this up slightly so we've got a bit more stuff to work with. There we are. Okay, so our timeline, so this is part II. Okay, so part II, our timeline now looks something like this. She has now still got the money coming in of 46,750, but now what's happening is she's taking the payment out here and here and here and here and here, and that's going to carry on forever and ever and ever. Okay, so that's going to go on forever and ever and ever. So what we have here is essentially the same sort of idea. Okay, so we've got to work out the monthly. We already worked out what the monthly payment, the monthly interest rates are, etc. So we're going to be using this time S of infinity is equal to a over 1 minus r. Now our a has changed. Okay, our a has changed this particular time because we've got to discount everything back. Okay, so everything's got to come back to the left. So here my a has now changed. Okay, it's going to be over here now. So what we have here is that this is going to be a, and I'm going to say again, let v equal 1 over 1 plus I. So what we have for this particular thing is we have av squared, av cubed, av to the power of 4, and so on and so forth. It goes av to the power of whatever. So you can see this particular time, what we have, instead of having a plus av plus av squared, which is up here, a plus av plus av squared plus av cubed, etc. What we have is we have av because we have one time period after that we've started to take the money. So this is now av, let's get back to here, av squared, av cubed, etc, etc, etc. So what we have this time is we have 477,500 is equal to av plus av squared plus av cubed plus av to the power of whatever. And yep, okay. I'm just going to keep going on to infinity. So what we need to do now is work out what my a and my r is. So this here is my a. We know that my r is just equal to v. And all we do now, guys, is throw it into the formula. Just going to just move this down a bit more again. Okay. So s of n, s of infinity, sorry, is equal to a over 1 minus r, which is going to be equal to 477,500. A is AV. Okay. R is V, so 1 minus V here is equal to 477,500. Again, guys, you're just going to stick it into the calculator. See what you get. It should be 46, not 47, shouldn't it? 46, I think. 46, I think. Apologies. Work out what's going on. Okay, and put it into your calculator, find what it is. You're going to get a number in front of A, divide by that, and you're going to get A is equal to 1830.08. And there is your answer. So she'll get that until essentially she dies. That's called into perpetuity. Okay, the last thing that you need to be able to do is what's called a bond, and this is a certificate issued by a government or a public company promising to repay borrowed money on a fixed date along with some interest at fixed intervals. It can be bought and sold on the open market, and look, we'll just see how these work. So a company wishes to raise finance to expand their operations. To do so, they issue a number of 10-year, 10,000 bonds that will pay 200 at the end of every 6 months, up to and including the maturity date. The current market interest rate is 4.5. What is a fair market value of one of these bonds? Okay, again, so we need to have a look at what's important here. So 10,000 is what they're issuing. They're going to pay 200 at the end of every 6 months. Okay, so 6 months this time. It's not yearly. So we're going to have to change the interest rate into 6 months. And it says up to and including the maturity date. So we're going to get 200 on that last maturity date. And if the current market interest is 4.5, what is the fair market value of one of these bonds? So the first thing we're going to do, again, is draw that timeline that I keep banging on about. Okay, so what's going to happen is you are going to give them some cash here. I'm going to call that here. I'm just going to put a little asterisk. So you are going to give them some money, and every 6 months they're going to give you 200. So at the end of every 6 months, so you get 200 here, 200, and that keeps going. Yes, you're going to get a whole load of payments over the 10 years. There's going to be 20 payments of 200, and then at the end, what happens is they are going to give you, because it says including the maturity date for the 200, they're going to give you 200 there. And they're also going to give you another payment on that date of 10,000, because that's what this means. If they're going to give you 10,000, they're going to give you this 10,000 in the future. That's what a bond is. So you also get, I'm trying to put this in, at the same time, you get 10,000 given to you as well. So just to recap on what that is. So you give them a certain amount of money today. They will then pay you €200 every 6 months for the next 10 years. Okay, and then at the end of the 10 years, what happens is you get €10,000 off them, and you now have to work out what is a fair price for this is. Now, guys, notice that everything is coming left, so it's all going to be discounted. Okay, so it's all discounted. So let's have a look at what's going on here. So what we have is we have a final sort of bill here, which is easy to work out, and then we have a series of payments of 200 for those 6 months. And we just have to add up those 200s, work out what the present value of that income stream of the 200s is, add it to the final payment of the discounted 10,000 for 10 years, and then we're done. So, first thing I need to do is I need to work out the 10,000. That's the easiest thing to do. So hopefully we can see the present value of the 10,000 payment is equal to, and it's just 10,000 divided by the interest rate, which is 1.045 here, and we've discounted it 10 years. We can use the AER there, and we just stick that into our calculators, guys, and that should be really, really nice. It's 6439.27682. So in order to get 10,000 in the future, that would be worth today 6439.27 or 28 cents. Okay. Now the next thing we need to do is just work out what all of these 200s are going to add up to. Remember, guys, this is not an annual interest rate. It is semi-annual. Okay. So or bi-yearly. So what we need to do is we need to change this into a bi-yearly or semi-annual rate. So what we do is we go to the side. And we see that's 1.045. And it's the power of a half minus 1. Because remember, normally we do it to the power of a 12th because we're working out per month. We only need 2 time periods this time, so it's the power of a half. And we stick that in our calculator and we get 0.02225241501 or something like that. Again, what I'm going to do now, guys, is just set up the fact that this is going to be discounted by 1 plus I, which is over there. This is going to be 1 plus I squared, and this last one is going to be 1 plus I to the power of 20, because it's coming back 20 particular places. I'm going to say let V be equal to 1 over 1 plus I to make this easier, just like I've been doing for a lot of these videos. And that means now I'm going to end up with this as an income stream with the 200s. So I'm going to end up with 200V plus 200V squared plus 200V cubed all the way over to 200V to the power of 20. Okay, so my A is equal to 200V. My R is equal to V. And again, guys, you'll have this all saved in your memory in your calculator. So it's just a case of running it through now. We know that S of 20 is equal to, and it's going to be 200V. 1 minus R, which is V to the power of N all over 1 minus V. You put that into your calculator, guys, and you are going to get the answer of, if you put it in, it's going to be 3,230 cents. Okay, now we need to add this and this together to see what it's worth at this particular time. Okay, so what would I give in order to get the 10,000 after 20 years and this income stream of 200? So if we add them together, the value of the bond is equal to 6439.28 plus 3,230 cents, and it's going to be 9639.58. So what that means is that for this to be absolutely fair, for nobody to win, that this would be worth €9,639.58 today for me to have this income stream. If I was offered this at a lower rate, so suppose that the company says we'll give this to you for 9,000, then I would say, yep, I'll definitely have that, because then I'd have a net present value of 639.58. If the company was trying to sell this for 10,000, I'd say, I want you to give me 10,000 here for this income stream, I'd be, no, go away.